Okay, so the recording has been started. So again, good morning, everyone. And this is lecture number 13, transformations of a strain. I know there's stresses in the slides, but we are now in the strain part. And so what we discussed last time is, let me just scroll to this one. So we discussed about transformation of plane strain, which means that in stresses, we can calculate stresses at a certain rotated axis. And for strain, it's the same thing. We have transformation of strain equations, which are the following. So I can calculate what would be the equivalent strain at a certain rotated axis. So for example, in this particular case, if I have elongation along my x and elongation along my y, or strain along y, I can uh, deduce what would be the equivalent strain at a certain angle, which is defined by this equation, similar for epsilon y prime. And we have all the similar equations, similar with our stresses, which are on the right side. So we have transformation of plane strain. We also have a graphical method. And we started the problem last meeting. We're going to continue that one. So for graphical method, it's almost the same way as the Mohr circle for stresses. It's just in this coordinate system, we have shear strain divided by 2, and we have normal strain in our x-axis. And the first thing for Mohr circle is about determining our normal strain. Our center using our normal strain average, and we can plot epsilon x, and now this one is shear strain xy divided by 2. Plot epsilon y shear strain positive divided by 2, and we have to find the radius, draw a circle, and determine the intersections in x-axis, which are your principal strains. If we have principal stresses, maximum and minimum, we also have principal strains, as we discussed, and the radius of our circle is this is shear strain in plane. Take note, this is in plane divided by 2 is equal to our radius, which means our in plane shear strain maximum is equal to twice the radius, because if this equation here is equal to r, so we have shear strain in plane maximum is equal to twice the radius. And we can also calculate for a certain rotation angle wherein we'll be able to determine or we'll be able to obtain our principal strains. So, and this is the process of doing that. And let's just jump to the problem that we started last time. So let's say you have this problem here. So we have epsilon along x. So that's a strain along x, strain along y, 320 mu, and you have shear strain xy negative 100 times 10 to the negative 6. So take note that this is times 10 raised to the negative 6, because we are talking about strain in the elastic region. So that's a really, really small strain. It's not in the plastic region, because the plastic region is, your material already deformed, so kind of it already failed, but this is more in the plastic region. And then we have a rotation angle, which is 30. So for this problem, so for the given plane state of for given state of plane strain, so use Mohr circle to determine the state of plane strain associated with axis x prime y prime rotated through the given angle theta. And this is a theta. It's counterclockwise, which means it's a positive angle. And we have this number, and we started solving it using transformation equations. Now for transformation equations, let me just go to the proper page in my notebook. Okay, it should be this one. Okay, so now the given are the following. Oops. Okay, so we have epsilon x is equal to 0, epsilon y is equal to positive 320, and again, this is times 10 raised to negative 6. So we have shear strain xy, which is equal to negative 100 times 10 raised to negative 6. And we have our theta, which is positive 30 degrees, because it's counterclockwise. Now we solve EX prime last time and using the transformation equation. And what we got is 36.7 mu. And how did we get it? So again, we are using equation right now. I know in the problem it's mentioned it's Mohr circle, but we want to solve it in two different ways so that I can show you the two different methods. So for equations, it's just using this transformation equation right here, which we kind of did last time quickly, I would say. So we just use this equation here, and what we got is epsilon x. So we have this value here, this value, which are given right here. We have this, we have angle, we have that number, which is 36.7 times 10 raised to negative 6. Don't forget this part right here, because if you're talking about strain of 36, that's huge. Strain is normally below 1, so that would be a lot of strain. Now, we also have epsilon y prime using the same the same transformation equation, the second one. So we have this, it's just minus right here, it's minus here, and then we're going to get a value which we defined as 283.3 mu. Now we're also asked to calculate for x prime y prime shear strain, which in this case, we're going to use this equation. So we have epsilon x, epsilon y, we have our angle, which is positive 30. We have this negative 100 times 10 raised to negative 6. And we have, again, 30 for our theta. And you should be able to calculate this number here. And I ask you to do that at home. So I assume that that should be all right. So it's just, again, substituting all those numbers to your equation. And this is at a certain rotated axis. It's not your principal strains, it's at a certain rotated axis. Now let's go to method number 2. So how can we apply Mohr circle for this specific problem? So this is method number 1 using equations. Okay. Now method number 2 is about using Mohr circle. So again, for Mohr circle, the first step is to calculate for center. So let's use method 2. So the first step is to calculate for center, which in this case, it's your epsilon average. So you have x plus y divided by 2, and that would give you 0 plus 320 times 10 raised to negative 6 divided by 2, and that should give you a value of 160. This one. Now, the center of your circle will be, so center will be 160 means 0. And if we're going to plot it right here, so that would be the center of our circle. Now, second step is to plot 2 different points. And in this particular case, we can plot epsilon x negative shear strain xy. And your x is 0. So you know that's 0. And that's negative. So negative shear strain xy, that's a negative 100. So that becomes positive 100, which means that, sorry, this should be over 2. Yeah, so you have to plot, so again, so I made a mistake there. So you have to plot epsilon x negative shear strain xy divided by 2, and that would give you, so this is negative 100, it becomes positive. Now that would give you positive 50 mu. So that would be your first point. So again, you are plotting this one right here. So instead of just shear strain xy, that's shear strain xy divided by 2, and that's negative. And your value here is negative, so that's why it becomes positive at the end. So that's your first point. And if we're going to plot our first point, that would be this one right here. Now that we plot the first point, the second point would be, oops, the second point will be, so plot epsilon y positive shear strain over 2. Now it's a negative number there, negative 100, so which would give us a second point, which is 320. So take note, your epsilon sub y is 320 mu, and your the second point, or this the y value would be negative 50. Now, if we're going to plot that one, this will give you this point here. So we have 320 positive number and negative 50, and that would be those 2 points. Now we can determine what would be the radius of our circle. So the fourth one would be determine the radius. And again, everything is just based on dimensions. So yeah, so if we're going to connect this, or before we connect this one, so let's imagine we have this points right here. So we can draw a triangle wherein we have, yeah, my triangle is not oriented properly, but anyway, yeah, so let's say we have here, so let's obtain this points right here. So from this point up to that point, this one, so I have a triangle. Now if I have a triangle there, this would be 50, that's 160. Now I can determine what would be my radius, and my radius would be is equal to square root of 160, and take note, you have times 10 raised to negative 6 right there, squared plus 50 square, and that would give you a value of 167.63. So that would be the radius of your circle. And now we have a radius, we can now draw a circle. Now, once we draw a circle, so we can connect those and then draw the circle here. Now, the question here is, what would be the values of your strain at a certain rotated angle, 30. So if we're going to rotate this one, the rotation should be 60 degrees counterclockwise. If this is 30 in your actual element, whenever you use Mohr circle, that's twice as much. So I have to rotate this one counterclockwise, and then I'm going to get this lines, and whatever the values at this point, I'll be able to obtain what would be my epsilon x or epsilon y. And take note, your 320 right here, this is epsilon sub y, which means if I rotate it at this point, the y value, or sorry, the x value. So take note, this is 320 is from your normal strain. That's normal strain value. So if I rotate it by 60 degrees in Mohr circle at this point, so I can take the value right here, and then I'll be able to obtain my epsilon y prime. So because this is epsilon y, and this rotation here from this point up to that point, that would be epsilon x prime. So now let's do it. So okay, so those are the points that we are talking about. So this would be epsilon y, epsilon x, and I put it right here. So the x component of this point, which is projected right here, that's epsilon x prime, and the other part would be epsilon y prime, because this is y, this is x, so that should be okay. And then I'm going to get the following. So I know the radius of my I know the radius of my circle, which are the following, and I can have this, for example, this triangle, and then I can obtain what would be the dimension of this, which is, of course, from this point up to that point, that would be the value of my epsilon y prime. From this point up to that point, that would be the value of my x prime, which are these points here. And I can label them as A, B, C, D, E, F, G right here, so that we can write those triangles. Now, let's write those triangles. So based on this, what we can, okay. So based on this one, so we have this triangle initially here. So this is the one that we use for radius. So I can label this one as, this is A, E, B. Now, if I'm going to use the same triangle, I can obtain this theta. Let's call it theta sub 1, for example. And why do I need this angle right here? In order for me to obtain what's this angle, because this, from this point up to that point, that's 60 degrees rotation. And if I know this angle right here, I have hypotenuse, I can calculate my length BF, I can add it to my center, and that would be the value for my epsilon sub y. And this same thing for the other side. If I know this angle here, I can obtain this length, and I can subtract it from my 160 value, and then I would be able to obtain this epsilon x prime. So let's do that. I know it's kind of straightforward, but let's do it. So tangent theta sub 1 is equal to, let's remove the mu for now, because they will cancel out anyway. That would be equal to 17.35 degrees, which means if that's 17.35, this angles right here would be, so I'll call it theta sub 2 for now. So that would be 60 degrees minus 17.35, and that would give you, so I'm talking about this angle for theta sub 2, and that angle would be 42.65. So now I would have the following shapes. So I have this triangle here, which I can call AEB, and they are labeled on the slide. So AEB, and I have this one here. So, and I can label it as D and C at this point. So we have D and C at this point. So this is just redrawing this section of your triangles right here. And I know that this angle here, of course, it's not scaled. This would be your theta sub 1, and this would be your theta sub 2. And then it's just basically taking out the dimensions. So now, okay. So if we do the calculation there, that would be epsilon. Okay. So this would be epsilon sub x. So epsilon x prime is equal to, so it's equal to this length right here, which is ED. So it's equal to ED, but that ED right there is equal to your epsilon average minus the minus the length DB right there. So okay, yeah, just checking. Yep. Sorry, that's one. Sorry, B. Yep, DB. Okay. And then you will get the following. So you have epsilon x prime. Just checking if that's correct. Yep. Okay. So that would be your center is 160 mu minus this BD right there, which is, if you check the angles, that would be equal to radius. And you can double check it at home. I know this is our just dimensional equations would be much faster for sure. Radius, okay, I'm not sure if you can see it. Cosine.
Excuse me, Professor. Do you mind? I don't know if you could zoom in or I'm having a little bit trouble reading what you're writing for.
Oh, okay.
Epsilon x prime equals. I'm not sure if that's a V or.
Okay, yeah, that's okay. Yeah, so I
Thank
can
you.
write it. No problem. So your epsilon x prime is equal to, so for this one, that's so we are talking about the x component, x prime. So we're talking about this point right here. So that's equal to ED, or it's the average, which is 160 minus the length dB. So which in that case, that would be your average is 160, this one, minus length dB, which we can obtain it by using this radius, using this angle, and that angle is this theta sub 2. So if we use our radius, so that would be the radius of our circle times, okay, so that's radius cosine of 42.65. Just checking if you can see that. Yep. So now once you calculate this one, that would be EX prime is equal to 36.7, which we did using equations earlier. So that would be for X prime. Now, how about for Y epsilon Y prime? So for Y prime, you can see that this is this point F. So we need to get what would be the X value at this point. So that would be the average, which is 160 plus this length right here from B to F. So which means that's equal to 160 plus, let's call it BF plus BF, and that's equal to 160 mu plus your BF is equal to radius. Oops, maybe you can't read it. Cosine 42.65. Now, take note that we know the radius, we know the values from the top, and that would be epsilon y prime is equal to 283 mu. And we calculated it earlier, so we have those numbers. Now, the question here is what would be the, for example, the value of your shear strain x prime y prime, and that's over 2, and that over 2 is equal to, you can see this length right here, that's your FG right here, or GF if you want to call it GF. So your y prime is equal to FG, and that's equivalent to, so it's R, so that would be radius sine, oh sorry, that should be radius sine 42.65. So that would be this one, and that would give you a value of x prime y prime is equal to 227 mu. So now you're able to get it based on the dimensions, and if we check the numbers on top, that would be the same values that you will get. So I'll just want to check. Oops, this value is at 227 mu, and take note that this a value right here is, that should be over 2. Yep, that should be over 2, and then eventually you will get 227 for your shear strain. Shear strain x prime y prime. So any questions at this point? Now, what if we tweak the problem a little bit? Let's say we want to so if you want to take to calculate for maximum and minimum, of course it's just the intersections of that circle. It should be the same way as stresses, but let's change the problem a little bit. Let's put some dimensions, and let's try to use the equation for strain as much as possible. So that we know that our strain is equal to L minus L naught divided by L naught. That's our description of strain. So let's try to see this problem, and then I'll ask you to solve some of it at home. But I'll give you the direction on how to solve this problem. So let's say we have a material in a state of plane strain. It is found that the horizontal side of 10 by 10 millimeter square elongates by 4 microns. So which means that if this one elongates in the horizontal side by 4 microns, this new length, so this is from 10, so initially this is 10 by 10. Now, the final length would be 10 by 10 plus 4 microns because it elongates by 4 microns. Now, its vertical side remains unchanged, so that's why this one is still 10. And the angle at the lower left corner increases by 0.4 times 10 raised to 3 radians. So it's very small angle. And it's shown in the figure that, okay, the angle increases so from 90 degrees, which is pi over 2 radians, now the angle is 0.4 times 10 plus. So the angle is now 90 degrees plus this radians right here. So the question is determine principal axis and strains and the maximum shearing strain and corresponding normal strain. So first, let's deduce what would be our strain state for this type of problem. So now we only have dimensions, but we know the equation for strain, so it should not be a problem at all. Now, if we look at the problem, or sorry, if we look at the strain along y, so it mentioned that the y, or the vertical direction, didn't change before and after applying the stress, which means I have a strain, oops, wrong pen. Okay, I'll call it problem 2. So our strain at y, we can call it 0 because it didn't change. So 10 after deformation, it's 10. Now, how about for x? So it mentioned that from 10, it becomes 10 plus 4 microns, which means I can calculate my strain in x, and we can apply this equation here. So your your final length, which is equivalent to 10 millimeter plus 4 microns. And take note, they have a different unit right here. So that's your final length minus your original length, which is 10 millimeter divided by 10 millimeters. So that would be the strain in X. And I forgot to point out that for this transformation or strain problems, we don't care about this very small angle. We are assuming that everything is aligned along X, even though in this particular problem, you can see that there is small angle. And take note that this is still exaggerating the angle. This is still huge angle compared to this 0.4 times 10 raised to 3 radians. So it's extremely small. So you can assume that everything just elongates along your X. So now let's calculate for strain along X. So you're going to find that this would be X would be equal to 400 times 10 raised to negative 6. In this particular case, I just force it to become times 10 raised to negative 6 so that I can call it epsilon x is equal to 400 mu right there. So I can simplify it into this one. So now I have my epsilon x and epsilon y. How about my shear strain? Now my shear strain is, so now my shear strain is about this displacement angle. And take note, we have a positive and negative shear. We discussed it before. So now what's a negative? What's a positive shear? So if we're going to recall, can you see that? Maybe not. Oh, you still can see it. Okay, so if we have, so this would be your positive shear. So if your positive edges, which are this, so if this is positive, that's positive, and the angle there from 90 degrees, it becomes smaller, that's positive shear. Now your negative shear is this one, and this is a negative shear because the angle in the positive faces of X and Y increases from 90 to 90 plus this radians, 0.4 times 10 raised to negative 3 radians. Now, so this is a negative shear strain. So how can I determine what would be the value of shear strain? So remember that if your angle is extremely small, and in this case, it's extremely small, most of these cases, because we are in the elastic region, we know that we simplified everything by assuming that our shear strain is equal to our angle or the additional angle in this particular case. And this should be in radians. Now we can say, based on this assumption, that our shear strain, if the displacement angle is so small, we can equate it to the value of shear strain. And that's exactly true if you're talking about deformation, which means that I can say that my shear strain in XY is just whatever this number right here, but in negative, negative shear. And that's negative. So my shear strain would be negative 0.4 times 10 negative 3. And take note that it's all not radians anymore because this is an angle and this is a strain. A strain doesn't have any units, and this is just an approximation. Of course, there's equation for shear strain if you have significant deformation. But in this particular case, it's so small that I can assume that it's just negative 0.4 times 10 raised to 3. That would be my shear strain. And I can further simplify it because I want everything to be having this mu right here so that everything would be consistent. It's much more convenient for me to play with the numbers. So I can now have a shear strain, which is equal to 400 times 10 raised to negative 6. And that's a negative number. Now I already have epsilon x, epsilon y, and a shear strain xy, and I can apply transformation equation to obtain my principal strains. Principal axis is theta sub b, and you have maximum shearing strain, which is in plane right now, in plane maximum shear strain, which is your gamma maximum in plane, and we have the corresponding normal strain at this specific position. Now, so let's just highlight what are those numbers. So we have this value here, we have this x here, and we have y equal to 0. So we have 1, 2, and 3. So those numbers will be used for inside using your transformation equations. Question at this point?
Yes, Professor. What would happen if the angle is large or sufficiently large? Would we? Is it even in? I don't know if it's in the scope of this class, but what will we do if it is a big angle?
If it's big angle, take note that you already applied permanent deformation. And for this class, we want to limit everything in the elastic region. So we're not going to tackle large angle. It's basically if you have large angle, your material already failed. And the objective of our class is to avoid failure as much as possible. So this angle right here would never be that large because we don't need deformation right now. What we are doing is we are limiting everything in the elastic region. And what do I mean by elastic? So let's say if your car is running on the bridge, it deforms. And if you don't know, that deforms for sure, and that's under the elastic region. If you overshoot it to your plastic region, your bridge will fail. So the answer there is it's not part of that. But yeah, we're going to deal mostly with small angles like this. Yep.
Okay, thank you, Professor.
Yep, no problem. Okay, any other question? So let's try to calculate that one. So the first question would be principal axis, which is, and let's use equation for now. There's more circle in the next slide, but let's just use more circle, and that simplifies a lot of things. So now we have A. So we are asked with principal axis, which means how much rotation I would need in order for me to obtain my principal strains. In this case, the question is asking for theta sub b. Now, it's also asking for the principal strains, which are epsilon 1 and epsilon 2. And we can easily check the equations in the previous slide. So if I move back to my slides, where are those equations? Okay. And you will see that should be next. So you will see that this is this equation here. So epsilon 1 and 2. So you have the average strain, average normal strain, plus minus square root of this quantity right here. I can use that equation, and then I should be able to calculate my principal strain. So let's do that. So, and after I calculate my principal strains, which are epsilon 1 and epsilon 2, I can calculate theta sub b by using this equation here. So I know my epsilon xy, I know my epsilon x and y, those are given. and I can calculate for theta sub p. So let's do that one. Okay. Okay, so let's do that. So now we have epsilon 1 and 2. Is equal to epsilon x plus epsilon y over 2. We're not going to substitute the numbers. I'm just going to write it right now. Is equal to epsilon x minus epsilon y over 2 squared. So just checking if you can see it. Yep. Plus xy over 2 squared. So you have that equation. I'm not sure if you can read that. Maybe not. Okay. It's 2. And then let's substitute it anyway. So that's 400. So your x would be equal to 400 mu plus 0 divided by 2 plus minus. So your plus would be your epsilon 1, which is maximum. Your minus would be your minimum. So square root of 400 mu minus 0 divided by 2 squared plus shear strain xy, which we calculated as negative. So we can call this one as negative 400 mu right there. So I can, this one is 400 divided by 2 squared. Maybe you can see it, but yep, you can at least see the 400 right there. And I'll send this file as well, so that should be all right. So you have sigma 1 and sigma 2 to be the following, or I can separate them. So I'm going to get the following numbers. So for epsilon 1, that would be 483. For epsilon 2 would be negative 83. So those would be my principal strains. How about my theta sub p? So we know that the equation for theta sub p is tangent to theta sub p is equal to xy shear strain x minus epsilon y. So I just copied it from the previous slide that I showed, and you will get the following. So you have 400 right here minus epsilon x is 0, and that would be minus 400, and you will get a value theta sub p, which is equal to negative 22.5, which means the rotation that you need is clockwise. So this is a clockwise rotation by a negative 22.5. So that would be your theta sub p. Now we have we answered letter A. How about letter B? So the maximum shearing strain. So let's deal with maximum shearing strain, and again that's in plane. So I need maximum in plane, and those are given in the equations again. So I'm going to go to the equation so that you will see where's that. If you go to the equations, there's a lot of animations here. Oops. So this would be the equation. So you have shear strain maximum divided by 2 is equal to this numbers right here. So I can use this equation. Let's write it down. So it's maximum, again, that's in plane, is equal to square root of epsilon x minus epsilon y over 2 squared plus shear strain xy divided by 2 squared. You can still see that. And substituting the numbers, and I'm not going to substitute it there. We can do the substitution there. You will get a maximum in plane, which is equal to 5. And take note that you have 2 right here. Don't forget about that 2. And that's a common mistake in the exam. So that would give you 566. So that would be your maximum in plane shear stress for this problem. But you have another problem here. So you're almost done with B, but there's another question. What would be the corresponding what would be the corresponding normal strain? Okay, you have the corresponding normal strain when you reach your maximum shear strain. So remember that when you are in the maximum shear strain, or let's say you are maximum shear stress, remember that. Okay, how can I explain this? So if you are in the maximum in plane, take note that your components for, so let's say, let's go back to our shear stress. So, and you should please know this one. So if you have in plane maximum tau for transformation of stresses, take note that at this particular location, your sigma x is equal to sigma y. That's always true if you are in the tau max in plane. And we showed it. If you go back to lecture number 2, you will see it from the waves that we plotted before. That if you track your maximum in-plane shear stress, if you check what's the value of the stresses at those points, you will end up with this number right here. So your normal stresses would be equal. It's similar to shear strain. So if we have a shear strain max in plane, your epsilon at that specific rotation angle or at that specific position would be epsilon x is equal to epsilon y. So your strains would be equal if you are at the position maximum in plane. And remember that we have the following relationship. So we have a relationship sigma x plus sigma y is equal to sigma x prime plus sigma y prime. So whenever we rotate our element, if you add the x and y components, that would always be equal. Same thing for a strain. So for strain, if I have x and y, whenever I rotate it to another angle, this would always be true. Which means that if I am at my maximum in-plane shear stress, which is 566 mu right there, I know that my strain or my normal strain at that point would be twice the normal strain is equal to epsilon x plus epsilon y. So take note that I'm assuming that this epsilon x prime and y prime, they are equal. So I can say that that's twice my epsilon, which means that I can now calculate for, where's that? Okay. I thought I calculated that, but anyway, yeah, maybe not. So now I can say that my normal strain is equal to epsilon x plus epsilon y, and we know that my epsilon x right here is, I think I didn't calculate it in my paper, but I should. So my x would be my y is 0, my x would be 400. So this is 400 and plus 0, normal strain 2. And that would be my normal strain at that point. Sigma epsilon x is equal to epsilon y, and that's equal to 400 mu divided by 2, and that would give me a value of 200 mu. So that would be my normal strain at when I'm at my maximum in-plane shear strain. Any question? Oh yeah, I did calculate it. I just can't track which one is which, but yeah, that's there. Any question? So again, the question here, if some of you are confused, is what would be the normal strain when you reach your maximum shear strain in plane? Question. So, but yeah, you can also solve this one using Mohr circle, and I'll leave this one to you to solve. So these are the numbers that we calculated based on the dimensions. So we have 400, we have 0, we have negative 400, and then if you use the dimensions there, you should be able to calculate for maximum and minimum by just using dimensional analysis. But again, yeah, most of the time, equations are much easier for sure. But for your exam, sometimes you will be asked for Mohr circle, sometimes will be asked for this. So unfortunately, you have to know both methods. Question?
Yes, Dr. Arnas.
Yeah, go ahead. Yep.
just at the end of the notes there, shouldn't that be epsilon x prime? And
Yeah,
epsilon.
okay.
Okay.
That's good. A good point. Yeah. Yeah. When you mentioned it right away, I check. Oh, yeah, that's correct. Yeah. That's true. So thanks for pointing that one out. So that would be x prime and y prime. Yeah. Thanks.
Thank you.
Yeah. Any question? Okay. So if none, we still have a 1 minute, but I'll just give you a. I would say topic that we're going to discuss for Friday. So for Friday, we're going to move to three-dimensional strain analysis. So we're going to check what would be, because let's say we're always talking about plane stress situation. If you have plane stress, you are applying stress in x and y. You are zero in z. But if you pull something or compress something, it will deform in three-dimensional ways. So your strain, it's not really plane strain. That's what we are doing at this point, assuming that it's plane strain condition. But remember that our assumption is we put the constraint, we are deforming it, but that's not, I would say that's not the practical approach. So we are going to do three-dimensional strain. So you're going to get epsilon x, epsilon y, epsilon z, and you can calculate those strains by using by using your Poisson's ratio, for example. But yeah, we're going to discuss it on Friday. So again, Wednesday, you're going to have your first quiz. And yeah, that's all for now. Unless you have any other, or if you have any question, just let me know.